Hi there, this is the first video about the new topic, refraction of light. Now, you've already done some work at National 5 and you should go back and revise that. One of the best ways to revise it is actually have a look at some questions. I've already posted some information about some Campbell-Robertson revision questions. You can tell the revision questions, they start with the letter R, and you'll find the details of those in the assignment. Right, so I'm going to start off with a definition of refraction, and a definitions need to be learnt. Okay, so refraction is the change in speed when light passes from one medium to another. Now, a medium just means a material, and it's just a posh word for material, but it's a physics word, and if you can remember that, fine. If you can't remember the word medium, just replace it with the word material. Refraction is the change in speed when light passes from one medium to another. So let's have a look at air. The speed of light in air is 3 times 10 to the power of 8 meters per second, and in glass, the speed, I'm going to put an A there, and I'm going to put a little g here, and it's about 2 times 10 to the power of 8 meters per second. So that's what refraction means, is you've got a change of speed. I think I'm just checking here, you don't have to remember these numbers, I have to look them up. You can have water. These are the common ones, which is 2.26 times 10 to the power of 8 meters per second. You'll get all these from the data sheet. You don't need to remember any of these. Well, you probably do remember 3 times 10 to the power of 8, but you probably won't remember the others. So if I've got a block of glass, and this is just revision from National 5, a block of glass, and I've got a beam of light that comes in, and it's in air on the outside, then it's doing 3 times 10 to the power of 8 meters per second on the outside, but it slows down. Now, you can't see this because this is so fast, 300 million meters per second. In glass, 200 million meters per second. But if you were to be able to film that and slow it down a tremendous amount, you would actually see this whizzing across here and then traveling pretty slowly in the glass, and then speeding up again on the outside when it gets back into the air. Right, find my rubber. You'll probably want to write some of this stuff down as we go. If I write it down, good idea for you to copy it down. Now, at the same time, and you would have seen this at National 5, at the same time when light goes from air into glass, that's if it goes straight on. If it goes straight on, it carries straight on. That sounds a bit strange, but if it hits the glass at 90 degrees to the surface, so this angle here would be 90 degrees just here. If it hits the surface at 90 degrees, it just carries straight on. But if it hits at an angle, it actually bends. So if I've got, instead of drawing a block, I'm just going to have like a boundary. The rest of the block's over here somewhere. Okay, but I've got a boundary. I've got glass over here, and I've got air over here. I'll get a ruler to do this because I need to do some stuff. In fact, I'll make that a nice straight line, and I'll do it in a different color. I need to do some reasonably neat drawings to show what's going on. So this is the boundary between air and glass blocks over here. And you'll remember some of this stuff. You need to do things like, let's draw a line at 90 degrees, and that's called the normal line. Now, if a ray of light comes in at an angle like this, here it comes at an angle, it's going to slow down when it hits the glass, but it doesn't carry straight on when it hits at an angle. It actually does not go straight on, but I'm just going to put in some very small dots here so you can see it doesn't go straight on. It actually bends round this way, bends towards the normal. I'm just thinking back, you would have done this back in first and second year when you would have shone some light on boards a bit like this with the red laser block over here, and you would have practiced shining some light through some blocks. You ought to be able to remember some names, and we've got the normal on there already. This is the incident ray. And this is the refracted ray. This is the angle of incidence. And we give that the letter I. Sometimes there's a number of different abbreviations we can use. I'm just going to use I for now because it's simpler. And I've got this angle here, which is our angle of refraction in there. And you need to remember that you always measure angles between the ray of light and the normal. Now, tests, SQA tests, block tests, that sort of thing, they try and catch you out sometimes. They would tell you what this angle is here, and perhaps this angle is like 70 degrees. But that's got nothing to do with what's going on. We're going to get on and we're going to do some sums, we're going to do some calculations. And if that was 70 degrees, that's not the angle you want. You actually want this angle in here. And if you know that this total angle is 90 degrees, then if that was 70, this would be 20. So you need to remember, always measure angles between the ray of light and the normal. So this is a sort of secondary thing about refraction. Primarily, the definition of refraction is that the ray of light changes its speed, but the ray of light can also change its direction. But that's not the definition of refraction. The definition of refraction is to do with the speed. So remember the definition of refraction. But light changes direction, and it only changes direction when it hits at an angle, because if it hits it straight on, it carries on straight. And that's still refraction, it's just it's slowed down in the glass. Light changes direction when it hits a boundary at an angle. And I'm going to do a little bit about why it changes its direction, which will help you. And we're going to move on now and look at these speeds as well, and what happens with the reduction in speed. So this is really all revision at the moment. I hope you'll remember that. Okay, so let's have a look at the change in speeds. Rub this out. You can carry on. You'll be able to see it on your page. And let's go back and have a look at air to glass, 3 times 10 to the power of 8, and 2 times 10 to the power of 8 meters per second. Okay, now there's a factor by which the light slows down. It was going at 3, and now it's going at 2. I'm just going to disregard the times 10 to the power of 8. So there's a sort of reduction factor which is actually 3 times 10 to the power of 8 divided by 2 times 10 to the power of 8. And if we disregard the 10 to the 8s, we get 1.5. Okay, if it's going from air into water, 3 times 10 to the power of 8, and I have to go back, I can never remember these, 2.26 times 10 to the power of 8. The reduction factor is 3 times 10 to the power of 8 divided by 2.26 times 10 to the power of 8. And I think that works out at 1.33. So this factor is bigger. Why is this factor bigger? It's bigger because the speed slows down by more. This one is a little bit less because the speed it slows down is less. 2.26 is nearer 3 than 2 is nearer 3. Now these numbers, these are quite important, these numbers, and these numbers, the sort of reduction factor is actually called the refractive index. And again, these numbers are in the data sheet. The refractive indices of the two speeds is called the refractive index. That's in the data sheet, and also the speeds are in the data sheet. So you could be asked to work out what is the refractive index when when light travels from air to glass, and you would just be able to do that simple sum, and you end up with the refractive index. So the refractive index tells you how much the speed is reduced. The bigger the refractive index, the more light is slowed down. That's an important thing to remember. The bigger the refractive index, the more light is slowed down. I don't know, I haven't got this one in front of me at the moment, but if you look up the refractive index or the reduction factor for diamond, for instance, diamond's a clear material, but it's very, very dense. And it slows down light even more. And I think the reduction factor or the refractive index for diamond is something over 2.4. So the bigger the refractive index, the more light is slowed down. And you would be able to work backwards, actually, if you knew the refractive index and you know the speed of light in air, you can actually then find out what the speed of the light is in the diamond. If I was to tell you that this is 2.4. You could work that backwards, but we would be doing more stuff like that later on. The bigger the refractive index, the more light is slowed down, and the more the light is bent. Now I'm saying bent, the proper word for bent is refracted, but of course this refraction thing has got two meanings. One is it's slowed down, so the more it's slowed down, the more it changes its direction, the more it's bent. So I'll change that to changes direction. Okay, and I'm going to show that in a diagram for you. Okay, so let's just we'll stick with air. A lot of these examples are air on one side and then some material on the other side, like glass, for instance, like water, and like diamond. Don't see too many questions where you're going from glass into water, for instance. We don't see that. So we've got our normal line. Let's put the normal line in. Put it down here somewhere, out of the way of the writing. Let's have our ray of light coming in, like this. This is the ray of light in air. We know that that number for glass is about 1.5. That refractive index is 1.5. We know it's 1.33, and I'm sorry, I should have looked up the number for diamond first, but I'll say it's 2.4. And then we can look at what happens to the beams of light. Okay, the bigger the number, the more the light is slowed down, and the more the light is bent, or the more the light changes its direction. Okay, so the number that's smallest, water, is 1.33. So the beam of light doesn't change direction too much. This is straight on, and it, of course, has got to change direction a little bit. So we could have water, the beam of light entering water would be like that. Glass, the number is a little bit bigger, so it slows down more and it changes direction more. So I could put this in, put it in as a slightly different line there. That would be if this material on the right is glass, and the number, the refractive index or the reduction factor for diamond is big. That means that the light slows down a huge amount and it changes direction the most. And that would be diamond, like that. Now I want to introduce some analogy so you know which way and what's happening and why. And the analogy that I've got that I sometimes use is to do with tractors. The farmers will enjoy this one. We've got tractors traveling along, and we've got a tractor not traveling along in the air, but we've got the tractor traveling along on some concrete. And tractors, believe it or not, can actually do about 10 miles an hour on concrete. But when they enter some sort of muddy field, and I'm going to have a boundary here, and I'm going to have mud on there, and I'm going to draw my tractor. My tractor could look a little bit like this, okay, just sitting there. It's a block, and it's got some wheels. So I'm going to draw a tractor coming along here. And the tractor's got some wheels sticking out. And before the farmers start complaining that the back wheels are bigger, I know they are. And this is no particular car. It's a blue tractor, which will please some people, but not others. Tractor Wars is on the Black Isle. You know, what colour's your tractor? And if it's not the right colour, there's usually some sort of fight at the Black Isle show and people get arguing about it. Right, so here I've got my, just ignore all that. Here I've got my tractor coming along like a beam of light, okay? And the beam of light has a width. I mean, everything's got a width here. If you zoomed in on this beam of light, it would actually be quite wide if you had a look with the microscope. So I'm just making the beam of light much wider that way. And this tractor's got wheels. I've got wheel A and I've got wheel B. Now, everybody ought to know that when a tractor goes from concrete, where it's traveling along quite nicely, it gets into mud, it's going to slow down. And of course, once the farmer's in the field, he can mess about with his gears. The light hasn't got gears, but we'll forget about the gears. But what's happening here is this wheel will hit the mud first and it will slow down first, whereas this wheel will keep going at the same speed. It's going at a higher speed. So what's going to happen here is this slows down first, wheel A. Wheel A slows down first, wheel B keeps going. It keeps going faster. So if this wheel slows down, it gets bogged down as soon as it enters the mud, but this wheel here is still on the concrete. this wheel gets driven forwards and the whole tractor actually turns round that way, and it's not pointing in that direction anymore. It gets turned round there, okay, as the wheels here enter the mud at different speeds at different times. And that's just the same with the air. Imagine this beam of light being much wider and being a beam of light waves that are perhaps this wide coming in here. As soon as this bit of the light hits the material, this bit changes speed and slows down, whereas this bit over here keeps going at the same speed as it was, and it swings round that way. So you've got your tractor coming in at this angle here, and then it's going to slow down and it's going to change. It's going to rotate round in that direction there. And if we just stick this normal line back in again over here, we can see that the tractor has changed direction, has moved around towards the normal. So when the beam of light slows down, it moves towards the normal. I'm going to rub this bit out and I'm going to write that down. It's another important thing I think you need to remember. So when a beam of light slows down, it bends towards the normal. Now, exactly the same thing would happen, but in the opposite direction when the tractor comes out of the muddy field. So we can imagine that it's right in the mud here, and it's then traveling in a straight line, but it's traveling slower, and then it gets out to the muddy field over here. Okay, and the same thing happens. The tractor, which is in the mud here, here's the tractor, here's wheel A, here's wheel B, got the wheels at the back. Okay, the same thing happens, but it's going to happen in the opposite direction. This is the mud, and then it goes back onto the concrete, goes back onto the road. Okay, this wheel is going to speed up first. This wheel is still going more slowly. Okay, so if this wheel speeds up first, it's going to swing it round back down this way because it's going to go faster. It's going to get a better grip. It's going to swing it round that way. This wheel is lagging behind, and so when the beam of light comes out the other side, here's our normal line again. The tractor is actually going to turn that way, and the beam of light is going to go back down this way. And I've not drawn that very well. In fact, it's rubbish. But the beam of light will actually go back and will be, if I can get this ruler worked out, it will be about parallel, and it will come out down there parallel to where it was in the first place. So when a beam of light slows down, it bends towards the normal. Think of the wheels. It goes up like that. And when the beam speeds up, it bends away from the normal. So what that means is that this is the angle of incidence here, and this is the angle of refraction, and you'll see that the angle of refraction is much smaller. As it bends towards the normal, the angle of refraction gets smaller. As it bends away from the normal, then that angle gets bigger again. All right, I hope that makes sense. So you can always use this idea of the tractor, and you can complete diagrams. So let's have a look at completing some diagrams. Let's just take a block, roughly speaking. Block's going to look like this. Okay, and you would have done this sort of thing. Okay, with blocks probably previously. Right, so here's the normal. Here's my beam of light coming in. And remember, it's going to swing towards the normal. There's the normal. Instead of going straight down, it's not going to go straight down. It's going to bend up this way. It's going to get closer to the normal. This angle of incidence here is going to be big. This angle of refraction is going to be smaller. When it gets to the other side, I can put in a normal again. And what's it do? This is air. Let's say this is air, obviously, on the outside. And this is glass here. And what's it going to do? It's not going to go straight on. This is straight on, but it doesn't do that. As it speeds up, the tractor's going to turn around. It's going to bend away from the normal. And remember, it comes out. Slide my ruler across, and it will come out parallel to where it was. And there's a diagram completed for you. So slowing down towards the normal, speeding up away from the normal. So it goes round that way when it slows down, round that way, away from the normal when it speeds up. So you can get the idea of that. That is what happens with a block like that. Let's have a look at what happens with a triangular block. I'm going to draw a nice triangle. Like this. Now, a triangular block of glass is called a prism, not a prism, not where you get locked up. It's called a prism. And we can have a look and see what happens to the changes of direction when the beam of light comes in. So let's have a beam of light coming in. Let's put a normal right here in the middle. Like that. We'll have a beam of light coming in like this. Here's my beam of light. Air on the outside. Glass on the inside. You should know prism. This is an equilateral triangle where all the angles are the same, and you should know in maths that the angles all add up inside these shapes to inside a triangle, certainly to 180 degrees. So the angle here is 60, and that's 60, and that's 60. If that's helpful, if you wanted to draw it really accurately, you could do so with a protractor. Okay, so the air is going at 3 times 10 to the power of 8 here. It's going to slow down until it's traveling at 2 times 10 to the power of 8 in the glass. As it slows down, it bends towards the normal. It does not go straight on. It turns towards the normal. So it's going to go from there, and it's going to turn something like that. There you go. Because it's going to bend towards the normal. And it's just the same rule that we had before. And then it comes across here. What's it going to do there when it comes across? Well, I think we should draw our normal line at 90 degrees. Try and get this right. And as it goes from the glass back out into the air, it's going to speed up. What does it do when it speeds up? Well, you had that written down before. As it slows down, it bends towards the normal, slows down, bends towards the normal. This is just what you've got written down probably higher up your page. As it speeds up, bends away from the normal. So I like to put this dotted line in as if there wasn't a boundary and it was going to go straight on, but of course it doesn't go straight on. This is if you're doing tech, this is like called a little construction line to help you draw it. It bends away from the normal. Well, there's the normal. It's not going to come out like that. It's going to bend further away from the normal down here. So the beam of light is going to come down like that. Okay, this is a little bit different to the block. I'll just go and do a sketch of the block. The beam of light came down there, went up there, came down like that, and the 2 rays, it's not really very good, but the 2 rays in air are both parallel and bends one way, and then it bends back again. Well, it does the same here, but because you've got the sloping sides on the glass block, it does not mean that this ray of light comes back out up here. This is a very common mistake that people make when they see these shapes. Right, so you have to put the normal in each time. You have to say to yourself, what's it doing? Slows down, bends towards the normal, speeds up, bends away from the normal. Okay, now what would happen if you replace this with, a diamond? Well, for a start off, I wouldn't be teaching to you, because a diamond of that shape would be extremely expensive, and I would have sold it. I would have made millions, and I'd be living on some nice sunny Caribbean island. But if this was diamond, okay, you could think what would happen. Now, reduction factor, or the refractive index, we've got that reduction factor 3 times 10 to the power of 8 in air, 2 times 10 to the power of 8 in glass. That gives us the reduction factor for glass, or the refractive index is 1.5. I don't know the speed of the light in the diamond, but it's much, much slower. So that means the refractive index, or the reduction factor, is much, much bigger. And I guessed it's around about 2.4. I suspect it's 2.42 or something. So what does that mean? If it went into diamond, it slows down even more. And bends towards the normal even more bending. So your beam of light, if this was diamond, you can see why I'm doing it in 2 colors here, it would bend even more, and the ray of light would come down here like this if the material was of a much higher refractive index. And then it comes back out, and it's been traveling really, really slowly, and then it suddenly speeds up, because its reduction factor is a big number. It slows down even more. So it's going to go back up from a really slow speed back up to 3 times 10 to the power of 8. You'd have to put in your normal line again, just to sketch what's going on. So I'll put the normal line in here like that. Okay, now that beam of light is not going to travel straight on. I'll put in my little construction line. Okay, it's going to speed up. Comparatively, it's going quite slowly, much more slowly in diamond than it is in glass. So it's going to speed up more when it comes out. Okay, so that means it's going to bend away from the normal even more. Okay, so we put even more in there, we'll put even more in there. Speeds up even more when it comes out, bends away even more when it comes out. So how can it bend even more? Well, you can bend even more if it comes out like that. Okay, like that. This in principle, and we'll cover this a little bit later on, this in principle is what happens with white light going into a raindrop. Raindrops have some sort of mildly triangular shape as a raindrop is falling, and white light that goes into a raindrop gets split up into its different colors, and that's called a spectrum, and we'll be doing a little bit more about that, the spectrum of light, and that's how rainbows are caused. So white light from the sun, when it's raining, enters a raindrop, and the different colors are slowed down by different amounts, and you get a spectrum of light here. Okay, we'll be doing that later on, and so I'll revisit that. Right, so I'm just going to stop a minute. I'm going to have a quick glug of tea here. Just try and keep up with myself with what's going on. Okay, now you're going to see these diagrams different way round. You might see the prism that way. You could see a prism upside down. You could see a block of glass where the boundary goes vertically and the prism is at an angle. What about just to mix it up a little bit. Let's have a boundary that goes like that, and we'll have air up here, and we'll have glass down here, and we'll have a beam of light coming in at an angle. I'll put my normal line in. I'll have my beam of light coming in here like that. There you go. What's going to happen as it goes from air to glass, it slows down and bends. Which way does it bend? It bends towards the normal. So instead of going straight on, it doesn't do that. It's going to come down here like that. And this is my angle of incidence, and this is my angle of refraction, like that. Okay, so I'm going to label that I, and I'm going to label that R. Now, the SQA, and indeed a lot of physicists, don't like using these letters I and R. Angle of incidence, it's obvious, angle of incidence is I, and the angle of refraction is R, but there are some alternative abbreviations, and they are, this is the Greek letter of the alphabet theta, and this is going to be called theta 1, and this angle here is going to be called theta 2. So we can replace I with theta 1, and we can replace R with theta 2, and theta 1 is going to be bigger than another mathematical symbol, bigger than theta 2. The angle of incidence is bigger than the angle of refraction as the beam of light slows down and moves towards the normal, changes direction. So just remember some rules. All angles are measured to the normal. Must always take the ray of light and then measure the angle towards the normal. What happens when it comes out? What happens when it comes out down here? I'm going to rub this bit out. I hope you've got that. Of course, you'll be pausing the video and doing that. What happens when the beam of light comes out? Let's have, basically our block's going to be here. All right, and the beam of light is going to continue like that. I'm going to put in my normal. And remember, the beam of light is going to speed up. It's going to, well, that works out quite nicely. The beam of light is going to speed up and bend away from the normal. Now, a bit of, I'll just take out that theta 2. It's taking up a bit too much room. Okay, so this is theta 2 here. Now, some simple geometry would tell you that this angle here is also theta 2. And this angle, because these two lines are parallel, that ray of light coming in there is parallel to that ray of light leaving. This must go back to being theta 1. Okay, so once again, theta 1 is bigger than theta 2. Angle of incidence, angle of refraction. This is why we tend to use theta 1 and theta 2. Otherwise, you're going to get mixed up here, because you might say, oh, this is the angle of incidence as it hits here, and then this is the angle of refraction. Well, it's not. So we're going to try and move away from I and R to theta 1. Theta 1 is always the bigger angle outside in the air. Theta 1 bigger than theta 2. Theta 1 is always in air. and theta 2 is in the medium or in the material, whatever it is, whether it's glass or water. And then we can always ensure that we're talking about the right angle. We don't have to swap round I and R, angle of incidence. Some people seem to think that this is the angle of incidence because it's coming into this boundary, but it's not actually. So we're going to forget I and R now. I'm going to move away from that. I'm going to try and get you to remember theta 1 is always in air and it's always bigger. Theta 2 is inside the material and it's always smaller. Theta 1 bigger than theta 2. In terms of density, air is not very dense and glass is. So theta 1 is in the less dense material, and theta 2 is in the more dense material, and the more dense material slows the light down. So less dense, that could be air there, that could be glass, could be water, could be diamond, and you can think about it in terms of density as well. So air, theta 1, whatever the material is, and there's a whole list of materials. Whilst I'm talking about the whole list of materials, there's a material that's called glycerol. And nobody knows what glycerol is, but it's a type of oil. So the SQA or tests can mix up what are these different materials. Is this glass? Is it water? Is it glycerol? Is it diamond? And all of these materials have got different reduction factors. They've got different refractive indices and they slow down the light by different amounts. The more dense, the more the light slowed down, the more the bending. Okay. I think that would be a good point to stop this introduction. I don't know how long that lesson is. I'll find out when I've stopped it, but I'll stop there, and this will be the first video lesson for introduction, the first lesson that is the introduction, that is refraction, the refraction lesson. So I'm going to call this Refraction 1, Introduction Refraction 1, and I will then go on to do the next video, Refraction 2, and there'll probably be a number of refraction videos. I know these videos are coming late, and they're coming after you've already received an idea of what the work is. Possibly not many of you have started the actual refraction work yet, and you might still be working on photoelectric effect. So you can pick these up, and I'm sorry these aren't coming in the right order with the work that I've already posted, and that's because of working from home and working in school with classes clash, and it just doesn't leave me time to do lots of recordings whilst I'm in school. So you'll have guessed I'm at home today. You can see by the background I'm at home. That's given me the opportunity, which wasn't the case earlier in the week. That's given me the opportunity to record some lessons. So I'm going to stop now, and then I'm going to go straight on afterwards, after I've had a short break and I've had my breakfast. I'm going to do refraction lesson 2, but I'll stop for now.